Hello, everyone. We're continuing with our grade 12 Physical Sciences 2023 November, paper 2, so chemistry. Questions 1 through 3 have been done in previous videos. In this video, we're going to look at just question 4. So, diving straight into it, this is still mainly organic chemistry we're looking at. The first question, so question 4.1. Consider the cracking reaction below. So the reaction is given, and firstly they want us just to define cracking. So unfortunately this is just something you'd have to memorize, a definition you'd have to memorize. Cracking is a chemical process in which basically longer chain molecules are broken down into shorter ones. So often, longer chain molecules are not very useful, um, and we would want them in shorter molecules. For example, when we have crude oil, there's a big mixture of very long chain molecules, and we might want to break it down into more useful gases like methane that we use like on our gas stoves or our heaters, propane as well, butane. So yeah, cracking is just breaking long molecules, as we can see here, C16, into shorter ones, C6, C6, and some unknown molecule there, which is probably shorter as well. So the next thing is write down the values of x, y, and z in the equation. So let's try and balance this. Let's try and balance this. Let's start off with x. So if we assume that uh, it's an alkane. So if um, this molecule here, let's assume it's an alkane. With that in mind, we remember that our equation for an alkane is CHN 2N plus 2. Um, as we can see here, we had 16. 16 times 2 is 32, plus 2 is 34. So this one here is definitely an alkane. This is an alkane. And this is also an alkane because 6 times 2 is 12 plus 2 is 14. So we'll just assume this is an alkane. And if it's C6, so subbing in C6, that means we will get H14 as well, right? So let's just see if this works. And let's keep a running total of our carbons and hydrogens. So at the moment, we started off with 16 carbons and we've used 12. So we only have 4 carbons left. And that means that this last molecule, Y, should be 4. So we have 2C, probably 2 to make 4, H6, if we assume it's it's an alkane as well. So let's do the math. Let's see. So we have H14 plus 14, that's 28, plus plus 12, that gives us 40 hydrogens, which is wrong because we only have 34 in the starting molecule. So that means our initial assumption here was incorrect, and this molecule is this molecule here is not a alkane. It might be an alkene. So let's try it. If we remember, an alkene is HN2N. So if we have C6, C6, H12, okay. So let's keep a running total of our carbons. So we've used 12 carbons, okay. Hydrogens, 14 plus 12, we've used 26. With that in mind, how many carbons are left? So 16 minus 12 leaves us with 4. Since we have a 2 outside, we definitely know the next molecule is 2C2. So that means we know that X is definitely 12 and Y is definitely 2. And then hydrogens left. So we started off with 34 and we've used 26. That means we have 8. And since there's a 2 outside, that means 4. So H4. So this is an alkene as well. And that means Z is equal to 4. So with some of these, you just gotta try it out and see what works. It's okay to make an initial assumption, even if it's wrong. That's fine. But yeah. So moving on to the next question. Compound C6H14 undergoes complete combustion. Write a formula to show this, a balanced equation. So complete combustion means that the entire molecule is broken down into carbon dioxide and water. If it was incomplete combustion, we might have other alkanes or alkenes in the products, and we might have carbon monoxide, not carbon dioxide. So we know that for combustion, we definitely need oxygen. We're just not sure how much yet. And we know that, if I just give myself some space, we know that our products, I'll just write it at the bottom, it's definitely going to be CO2 plus H2O. We're just not sure how much of each right away. So the first thing to notice here is we have 6 carbons. So there has to be 6 carbons on the right-hand side of the equation. So here we definitely have 6. And then we have 14 hydrogens. So there has to be 14 here as well, which means this is 7. Now, with this in mind, if we count the oxygens, this gives us a total of 6 times 2, 12, and 7 times 1, 7. That's 19 oxygens in total. Okay. So now 19 is a bit of a weird number. It's not an even number divisible by 2. So what we'll just do, instead of writing 9.5 here, which you can technically put 9.5 there, we'll just work with whole numbers. It's a lot easier. We'll just multiply everything by 2, which means we will get 9.5 times 2, which is 19 here. And since we're multiplying everything by 2, we'll get a 2 in front. And then 6 times 2, we'll get 12. And then 7 times 2, we'll get 14. And this is our balanced equation with the stoichiometry 2, 19, 12, 14. Okay. So whilst it is correct to say 9.5, sometimes it's just easier to work with whole numbers. And then you just say, yeah, multiply everything by 2 to get it to be like nice round whole numbers. Okay, moving on to the next question, question 4.2. Consider the equation below. So the reactions 1 through 3, A and B represent organic compounds that are positional isomers. X is an inorganic product. Okay, so there's some important information here. X is an inorganic product. A and B are positional isomers. All right, let's get into the question. So define a positional isomer. So you can phrase it however you like. You just have to include some key information, which is all isomers must have the same atoms. So the molecular formula is the same. That's true for any isomer. So compounds with the same molecular formula, but different positions of the side chain. So the arrangement is different. Positional isomers means it's pretty much the same compound, except, for example, you can have 1 butanol or 3 butanol. Technically, one is like a tertiary alcohol, one is a primary alcohol, so they are very different properties, but they are positional isomers in that they have the same molecular formula, but the OH group is positioned in different places. So on the chain, in 1 butanol, the OH group is at the end, and in 3 butanol, it's in the middle of the chain. So yeah, you can phrase it how you like, but compounds with the same molecular formula, but different positions of the side chain, I suppose, substituents or functional groups. So the butanol example, it's different positions of functional groups. Okay, type of reaction represented by reaction one. So let's have a look at reaction one. We have some organic compound reacting with acid to give A and B. So often these types of reactions, unfortunately, you just have to memorize this. It can be a halogenation reaction, like we could be substituting the Cl somewhere into this molecule. It could be an addition reaction as well, that's also correct. And instead of saying halogenation, you can be more specific and say hydrochlorination, because we're dealing with a chloride ion being added to this chain. So all are correct. You could say it's simply an addition reaction, which is true. Hydrohalogenation, because this is a halogen, or hydrochlorination to be specific, because this is chloride. Unfortunately, you just have to memorize that and just know and be able to recognize when you're adding something to this compound. It's hard to see, but there is a double bond here. This is an unsaturated molecule. So HCl can attack that double bond and add hydrogen one side and Cl the other side. So it's definitely an addition reaction. Okay. Question 423. What is the structural formula of compound B? Okay, so we kind of gotta like now work out this this reaction. So let's have a look at, let's first draw what let's draw out the equation. So we have CH3, CH2, CH, and then double bond CH, and then at the end CH3. Or just to be consistent, I'll just draw in the sticks that represent hydrogen. And then we have HCl. And definitely what we know is that HCl is adding across this double bond. So from the information they told us, A and B represent organic compounds that are positional isomers. X is an inorganic product. So what you can see is that there are a couple different ways that HCl can add across the double bond. Specifically, it can add, so I'll just like say R to represent that, and this is, we'll just call this R1 just to make it easier. So call that R2. So it can add this way. This becomes a single bond on the same side. So HCl is added on the same side. Or it can add on different sides. So R2, yeah. So we'll have the Cl on the other side. Essentially, oh, my mistake. When I say the other side, I mean this side. So because R1 and R2 are different, they're not the same. As you can see, this is one carbon, this is two carbons. R1 and R2 are different. Technically, you have a different molecule if Cl adds closer to R1 or if it adds closer to R2. So the answer to this question, yeah, is basically these. This is A and B. It doesn't matter which way you denote it. You just have to draw this. Either answer would be correct. But I guess the trick to this question is just realizing why there are two products when if you ignore the isomerism, you just expect one final product, but they throw in A and B to confuse you. So you just have to realize they're the same thing. It's just chlorine is adding different carbon. So whichever way you draw it, any answer would be acceptable for B, because there's no way of knowing which is which. All right. So the next question, write down the formula of X. So what is X? So we have some starting molecule where it says, ah, okay, so we know what A is actually. It's this molecule with HCl added across it. So it's a haloalkane, and then it's reacted with water and heat. Um, and this is basically a condensation reaction or hydrolysis, which means we're gonna like either add OH and essentially displace the chlorine atom. So if we have HCl added here and then we react with heat and water, this triangle just means heat, and then we basically substitute the Cl for the OH. Essentially, we're going to regenerate HCl. So you don't have to like work through this. You should just be able to see that from this reaction, we're just going to regenerate HCl. So the formula of X is simply HCl. We're going to regenerate the acid. Inorganic reagent for reaction 3. So now we take our alcohol. It seems it's a secondary alcohol, I think. And we're going to basically regenerate our alkene plus water. So the question is saying the inorganic reagent for reaction 3. So what reagent um, can regenerate our alkene and the water? Unfortunately, you just gotta know this. It's strong base. So any strong base. You could just say concentrated strong base or strong base. Um, it has to be strong though, it can't be dilute. So whether you say strong or concentrated, but any base. So there's a whole host of options. You can say lithium hydroxide, sodium hydroxide, any case. But this, unfortunately, you just have to know that an alcohol plus strong base is going to give you an alkene and water. This is a condensation reaction. So I think I said two was a condensation reaction. That's wrong. Two is a substitution reaction. This was substitution. This is condensation, and this is addition. So you just have to memorize these reactions and what reagents work with them. Unfortunately, there's no tricks. You just have to know the answers. Um, all right, moving on to 4.26. Compound A can be converted directly to an organic product, to the organic product of reaction 3. So compound A, which is our haloalkane with chlorine, can be converted directly back to an alkene. So besides heat, write down the reaction conditions needed to do this. Um, oh, my mistake. Sorry, I got a bit confused here. Um, in order to convert this alcohol back into an alkene, it's not strong base, it's strong acid, specifically sulfuric acid. So this is concentrated H2SO4. H2SO4. Yeah. Then the strong base comes in for converting the haloalkane directly back into the alkene. So the product of reaction 1 to the product of reaction 3. So for here, this is where the concentrated base comes in. So I got a bit mixed up there. It's very easy to get mixed up with all these reagents, all these different things you just have to memorize. It's useful to write down a crib sheet and just like memorize it, and practice it, so that you don't make these mistakes like what I just did. You see how easy it is to get confused. Okay, so finally, the last question. Write down two terms that describe this type of reaction. So essentially, the reaction of converting the haloalkane directly back into the alkene, you can think of it as I am eliminating some atoms from the molecule. So it would be correct to call it an elimination reaction. You could also, so that's one term. You could also say just as we hydrochlorinated it in the first reaction. So the alkene reacting with acid, it was hydrochlorinated. You could say by removing the chlorine and regenerating the alkene, we are dehydrochlorinating it. So that is also correct. Dehydrochlorination is also correct. Dehydrochlorination. Yeah, chlorination. Um, yeah, I think it's spelled this way with an I here. Dehydrochlorination. Yeah. So that's also correct. And just as we halogenated it or hydrohalogenated it, you could also say dehydrohalogenation, because you're removing the halogen atom, which is the chlorine. So yeah, this question is just about testing how familiar you are with the different types of reactions, some of the reagents. It's a question that tests your memorization. There's very few tricks here. You just have to like know these equations, these reactions, be able to recognize the different reactions. And this is a type of question that just purely relies on memorization. And that concludes question 4.